For the most part up to this point, we have been talking about atoms, formation of molecules, and their relationships. Yet we cannot forget the crucial part of studying chemistry, chemical reactions, how molecules interact with each other under specific conditions. However, before we talk about energetics, kinetics, or even classifications of chemical reactions, let's discuss the stoichiometric relationships we can derive from a presented chemical reaction. To start, let's discuss the characteristics of a written reaction. Reactants, or the starting materials of a reaction, are presented on the left-hand side of a reaction arrow, an arrow that helps split the reactants and products, or the molecules formed throughout the specific reaction. Reaction arrows help describe the conditions and flow of a chemical reaction. A forward reaction arrow signifies a reaction that only reacts one way, where an equilibrium reaction arrow, pointing both ways, represents a reaction that can flow from reactants to products and form products back to reactants. Moving forward, the most important relationships we can build from chemical reactions are dependent on the law of conservation of matter, which states that throughout a chemical reaction, matter is not created or destroyed. So if you have a certain number of atoms in the reactants, there must be that number of atoms in the products, or at the end of the reaction. The atoms can be in different states, within newly formed molecules, or even by themselves removed from their initial substance, but they must be there. Balancing a chemical reaction is the process of looking at the subscripts and coefficients of the molecules in the products and reactants and ensuring that the number of atoms are the same. This is extremely crucial to chemistry, and it's something that we'll be referring to time and time again. So let's start with our first example, formation of hydroiodic acid from iodine and hydrogen. Through just writing out the reactants and products, we can see initially that it's not balanced. There's one iodine and hydrogen atom in the molecule of hydroiodic acid within the products. Yet since iodine and hydrogen are both diatomic, there's two iodine and hydrogen atoms in the starting material. So in order to balance the reaction and make sure that there's equal amounts of iodine and hydrogen atoms on both sides of the reaction arrows, we need to change the molar coefficients of the products to better represent what is happening in the reaction. So, by placing a 2 in front of the products, we now have a balanced chemical reaction that reads, for the reaction of 1 mole of iodine and 1 mole of hydrogen will form 2 moles of hydroiodic acid. Another note, chemical reactions are represented in the lowest ratio, so always keep an eye out if you could simplify the ratio of reactants and products further. For example, if we had balanced the equation to equal 2 moles of iodine and hydrogen for 4 moles of hydroiodic acid, we could have divided all the molar coefficients by 2 to simplify the ratio and balance the equation completely. We need the reaction to be in the simplest balanced ratio to build reliant molar relationships from the equation, meaning that once an equation is fully balanced, we can confidently refer to the molar relationship of reactants compared to products and vice versa. For example, the benefit of building a molar relationship through balanced chemical reactions is learning how the reactants are used to form a product. Because just like baking, one of the ingredients is always going to be an excess and left over after the baking is done, where other ingredients are going to be used up entirely. In chemistry, the ingredient that is used up entirely is referred to as the limiting reactant. Through having a balanced chemical equation and knowing the amount of our starting materials, we can find the limiting reactant and find the theoretical maximum yield of a product formed for the amount of starting materials through relying on the molar relationships of an equation. For example, let's say we had a starting conditions of 3 moles of hydrogen and 3 moles of nitrogen. Under these circumstances, which reactant would be used up entirely in the formation of ammonia? In order to do this, we need to compare the amount of product each reactant could theoretically form. By comparing them to the same product, we could find which one would create less, hence the reactant that we used up first throughout the reaction. In previous molar relationships, we have been able to find the number of moles per gram or the amount of grams per mole. Yet within the equation, we could take any molar quantity over the amount of another reactant or product to build a conversion. This can help us find the limiting reactant. In our set example, we could take our starting 3 moles of hydrogen and multiply it by a ratio of 2/3, 3 moles of hydrogen to 2 moles of ammonia, from our balanced equation, to know the amount of ammonia it would produce, and perform the same step with nitrogen. Multiply 3 moles of nitrogen by 2 since the relationship of nitrogen to ammonia is 1 mole of nitrogen or 2 moles of ammonia. So we get this: 2 moles of ammonia produced from 3 moles of hydrogen, 6 moles of ammonia produced from 3 moles of nitrogen. Because hydrogen forms less product, it's the limiting reactant, what's going to be used up under the set conditions and represent the theoretical maximum yield of ammonia. The set conditions are important. Do not just go off of the different molar quantities in the balance equation, but the relationship between specific reactants and products to find the limiting reactant. So in the final example and practice question of this video, let's type everything we're learning and expand what we can find with the information we calculate. Question: let's find the limiting reactant of the combustion of ethane if we had 0.5 kilograms of ethane and 0.5 kilograms of oxygen. The reaction of ethane and oxygen to form water and carbon dioxide. Before we even consider moving forward, we have to make sure that the reaction is balanced. If not, all our relationships we build will be incorrect. On both sides, we have 4 carbon atoms, 14 oxygen atoms, and 12 hydrogen atoms. So our reaction is balanced. So let's set up the relationships and conversions we need to find the limiting reactant. And since we should refer to the same product, so we can actually compare them to find the limiting reactant. So for this problem, let's compare the amount of carbon dioxide produced. For ethane, we need to convert kilograms to grams, grams to moles of ethane using its molecular mass, moles of ethane to moles of carbon dioxide from our relationship of the balanced chemical equation. In this case, it's a multiple of 2. Then convert moles of CO2 to grams of CO2, finishing at 1,463.58 grams of CO2 produced for 0.5 kilograms of ethane. For oxygen, we convert to grams, moles of oxygen, then a 4/7 ratio of oxygen to carbon dioxide, then moles of CO2 to grams of CO2 for a final 392.95 grams of CO2 produced. It's clear to see that these conditions that oxygen is the limiting reactant, meaning that this amount of starting materials is the theoretical yield of CO2 produced in the reaction, 392.95 grams of CO2. And now that we know that oxygen is the limiting ingredient in the reaction, we can perform the same steps for the amount of water produced to gain a holistic understanding of our theoretical maximum yield of all products. Yet, as with all things, this is a theoretical yield and not a practical one. Mistakes happen, spills happen. So when performing reactions, we compare our actual yield, the amount actually gathered in the lab, with the theoretical we calculated on paper. So let's do this with water as an example. Let's say we perform this combustion reaction in the lab and have a resulting 0.19 kilograms of water produced. Let's compare it with the theoretical to know our percent yield. Dividing the actual yield of 0.19 kilograms of water by our theoretical 0.24 kilograms of water and multiplying by 100, we get a percent yield about 79.2%, which in perspective is really good yield. So I hope this deep dive into balancing chemical equations and finding the limiting reactant was really helpful with your studies. In the next general chemistry video, we're going to dive into 3 unique examples of balancing chemical equations and finding the limiting reactant. Remember, all these graphics can be downloaded from my website for free, and I truly hope you guys have a great day. See ya!